4-6. The Reynolds Transport Theorem. In thermodynamics and solid mechanics, we often work with a system, also called a closed system, defined as a quantity of matter of fixed identity. In fluid dynamics, it is more common to work with a control volume, also called an open system, defined as a region in space chosen for study. The size and shape of a system may change during a process, but no mass crosses its boundaries. A control volume, on the other hand, allows mass to flow in or out across its boundaries, which are called the control surface. A control volume may also move and deform during a process, but many real-world applications involve fixed, non-deformable control volumes. Figure 4-53 illustrates both a system and a control volume for the case of deodorant being sprayed from a spray can. When analyzing the spray process, a natural choice for our analysis is either the moving, deforming fluid, a system, or the volume bounded in the inner surface of the can, a control volume. These two choices are identical before the deodorant is sprayed. When some contents of the can are discharged, the system approach considers the discharged mass as part of the system and tracks it, a difficult job indeed. Thus, the mass of the system remains constant. Conceptually, this is equivalent to attaching a flat balloon to the nozzle of the can and letting the spray inflate the balloon. The inner surface of the balloon now becomes part of the boundary of the system. The control volume approach, however, is not concerned at all with the deodorant and had escaped the can other than its properties at the exit, and thus the mass of the control volume decreases this process while its volume remains constant. Therefore, the system approach treats the spraying process as an expansion of the system's volume, whereas the control volume approach considers it as a fluid discharge through the control surface of the fixed control volume. Most principles of fluid mechanics are adopted by solid mechanics, where the physical laws dealing with the time rates of change of extensive properties are expressed for systems. In fluid mechanics, it is usually more convenient to work with control volumes, and thus there is a need to relate the change in a volume to the change in a system. The relationship between the time rates of change of extensive properties for a system and for a control volume is expressed by the Reynolds Transport Theorem, which provides the link between the system and control volume approaches. Figure 4-54. The Reynolds Transport Theorem provides a link between the system approach and the control volume approach. The Reynolds Transport Theorem is named after the English engineer Osborne Reynolds, 1842 to 1912, who did much to advance its application in fluid mechanics. The general form of the Reynolds Transport Theorem can be derived by considering a system with an arbitrary shape and arbitrary interactions, but the derivation is rather involved. To help you grasp the fundamental meaning of the theorem, we derive it first in a straightforward manner using a simple geometry and then generalize the results. Consider flow from left to right through a diverging expanding portion of a flow field as sketched in figure 4-55, a moving system and a fixed control volume in a diverging portion of a flow field at times t and t plus delta t. The upper and lower bounds are streamlines of the flow. The upper and lower bounds of the fluid under consideration are streamlines of the flow, and we assume uniform flow through any cross-section between two streamlines. We choose the control volume to be fixed between sections 1 and 2 of the flow field. Both 1 and 2 are normal to the direction of flow. At some initial time, t, the system coincides with the control volume, and thus the system and control volume are identical, the greenish shaded region in figure 4-55. During the time interval delta t, the system moves in the flow direction at uniform speeds v1 at section 1 and v2 at section 2. The system at this later time is indicated by the hatched region. The region uncovered by the system during this motion is designed as section 1, part of the control volume, and the new region covered by the system is designated as section 2, not part of the control volume. Therefore, at time t plus delta t, the system consists of the same fluid, but it occupies the region control volume minus 1 plus 2. The control volume is fixed in space, and thus it remains remains in the shaded region marked control volume at all times. Let B represent an extensive property such as mass, energy, or momentum, and let B equal to capital B over M represent the corresponding intensive property. Noting that extensive properties are additive and the extensive property capital B of the system at times t plus t and t plus delta t is expressed as B system 1 equal to B control volume 2. The system and control volume coincide at time t, and B system t plus delta t is equal to B control volume t plus delta t minus B1 t plus delta t plus B2 t plus delta t. Subtracting the first equation from the second one and dividing by delta t gives B system minus B system t over delta t equal to the B control volume t plus delta t minus B control volume t all over delta t minus B1 t plus delta t over delta t plus B2 t plus delta t over delta t. Taking the limit as delta t approaches 0 and using the definition of derivative, we get dB system dt is equal to dB control volume dt minus the mass minus the rate B in minus the rate B out. Or B system bt is equal to B control volume dt minus little b rho VA plus little b 2 rho 2 V2 A2. Equation 4-38 states that the time rate of change of the property B of the system is equal to the time rate of change of the control volume plus the net flux of B out of the control volume by mass crossing the control surface. This is the desired relationship since it relates the change of a property of a system to the change of that property for a control volume. Note that equation 4-38 applies at any instant in time where it is assumed that the system and the control volume occupy the same space at that particular instant in time. The influx B in and outflux B out of the property B in this case are easy to determine since there is only one inlet and one outlet, and the velocities are approximated normal to the surface at sections 1 and 2. In general, however, we may have several inlet and outlet ports and the velocity may not be normal to the control surface at the point of entry. Also, the velocity may not be uniform. To generalize the process, we consider a differential surface area dA on the control surface and denote its unit outer normal by n vector. The following rate of property B through dA is rho B velocity vector unit outer normal since the dot product velocity vector and gives the normal component of velocity. Then the net rate of outflow through the entire control surface is determined by integration to be figure 4-56. Figure 4-56. The integral of lowercase b rho dot product velocity vector and unit outer normal vector dA over the control surface gives the net amount of the property B flowing out of the control volume into the control volume if it is negative per unit time. An important aspect of this relationship is that it automatically subtracts the inflow from the outflow, as explained next. The dot product of the velocity vector at a point on the control surface and the outer normal at this point is equal to the absolute value of the velocity vector times the absolute value of the outer normal cosine theta equal to the absolute value of the velocity vector cosine theta, where theta is the angle between the velocity vector and the outer normal as shown in figure 4-57. For theta less than 90 degrees, cosine is greater than 0 and thus the velocity vector is greater than 0. For outflow of mass from the control volume and for theta greater than 90, cosine of theta is less than 0, and thus the dot product of the velocity vector and outer normal is less than 0 for inflow of mass into the control volume. Therefore, the differential quantity, rho little b, dot product, velocity vector, and outer normal, dA, is positive for mass flowing out of the control volume and negative for mass flowing into the control volume, and its integral over the entire control surface gives the rate of net outflow of the property b by mass. The properties within the control volume may vary with position in general. In such a case, the total amount of property b within the control volume must be determined by integration, as given in equation 4-40. B, control volume, is equal to the integral over the control volume of rho b d volume. The term dB CV dt in equation 4-38 is equal to d dt of the integral of the control volume rho b change in volume, and represents the time rate of change of property B, content of the control volume. A positive value for dB CV dt indicates an increase in the beta constant, and a negative value indicates a decrease. Substituting equation 4-39 and 4-40 into equation 4-38 yields the Reynolds transport theorem, also known as the system to control volume transformation for a fixed control volume. Since the control volume is not moving or deforming with time, the time derivative of the right-hand side can be moved inside the integral, since the domain of integration does not change with time. But the time derivative in this case must be expressed as a partial derivative over partial derivative time, since density and quantity B may depend not only on time, but also on the position within the control volume. Thus, an alternate form of Reynolds transport theorem for a fixed control volume is given by equation 4-42. It turns out that equation 4-42 is also valid for the most general case of a moving and/or deforming control volume, provided the velocity vector is an absolute velocity as viewed from a fixed reference frame. Next, we consider yet another alternative form of the Reynolds transport theorem. Equation 4-41 was derived for a fixed control volume. However, many practical systems such as turbines and propeller blades involve non-fixed control volumes. Fortunately, equation 4-41 is also valid for moving and/or deforming control volumes, provided the absolute fluid velocity in the last term is replaced by the relative velocity, v sub r. Relative velocity v sub r is equal to v minus vcs, where v sub s is vcs is the local velocity of the control surface. The most general form of Reynolds transport theorem is thus equation 4-44. Note that for a control volume that moves and/or deforms with time, the time derivative is applied after integration in equation 4-44. As a simple example of a moving control volume, consider a toy car moving at a constant absolute velocity, v car equal to 10 kilometers per hour to the right. A high-speed jet of water, absolute velocity equal to 25 kilometers per hour to the right, strikes the back of the car and propels it, as shown in figure 4-59, Reynolds transport theorem applied to a control volume moving at constant velocity. If we draw a control volume around the car, the relative velocity is 25 minus 10 equal to 10 kilometers per hour to the right. This represents the velocity at which an observer moving with the control volume, moving with the car would observe the fluid crossing the control surface. In other words, v sub r is the fluid velocity expressed relative to a coordinate system moving with the control volume. Finally, by application of Leibniz's theorem, it can be shown that the Reynolds transport theorem for a general moving and/or deforming control volume is equivalent to the form given by equation 4-42, which is repeated here. An alternate of the Reynolds transport theorem for a non-fixed control volume. In contrast, equation 4-44, the velocity vector in equation 4-45 must be taken as the absolute velocity as viewed from a fixed reference frame. In order to apply to a non-fixed control volume, during steady flow the amount of the property B within the control volume remains constant in time, and thus the time derivative of equation 4-44 becomes 0. Then the Reynolds transport theorem reduces to equation 4-46. Note that unlike the control volume, the property B, content of the system, may still change with time during a steady process. But in this case, the change must be equal to the net property transported by mass across the control surface, an advective rather than an unsteady effect. In most practical engineering applications of the Reynolds transport theorem, fluid crosses the boundary of the control volume at a finite number of well-defined inlets and outlets. In such cases, it is convenient to cut the control surface directly across each inlet and outlet and replace the surface integral based on the average values of the fluid properties crossing the boundary. We define rho average, B average, and V sub r average as the average values of rho, B, and V sub r respectively. Across an inlet or outlet of control section A, the surface integral in the Reynolds transport theorem, when applied over an inlet or outlet of cross-sectional area A, is then approximated by pulling property B out of the surface integral and replacing it with its average.